Okay, let's start to recap what we learned last week. We covered some of the basics of performance analysis last week. So let's recap the basic theory about performance analysis. When we talk about performance analysis, we typically talk about a bit error rate. Okay, for any wireless system or any communication systems, when you talk about performance, that means two things, in fact. One is the capacity, the other thing is the bit error rate. Okay, for capacity, or some people call that the throughput, you want to increase it. The better, the higher the better, right? So you want to maximize the capacity or the throughput. So that's one of the performance metric. The other performance metric, which is more popular, is the error rate. For error rate, you want to reduce it. Okay, you want to make it small as possible, right? That's the goal. But in order to judge what is the BER for the current system, or suppose that you propose a new system, you want to investigate what will be the BER for that particular system. So to do that, we need to understand these basic theory on the performance analysis. Okay. So things can start from binary transmission. All of you probably know all these things, but let's review some of the basics. So we have a antipodal binary transmission. We have antipodal. Antipodal means that you have positive, negative energy. This is like +1, -1, and things like that. Right now we start from a AWGN channel, so there's no fading channel. There's no H. So your symbol is only added with the noise. So this is your symbol S, and you add a noise right here. And typically noise we assume as a Gaussian, AWGN noise. So therefore, even though you transmit this one, the receiver is not receiving this one perfectly because there's a noise. So because of noise, think about the Gaussian distribution. And think about the three-dimensional, like a mountain around here, right? So this one, when you add the noise, this symbol can be received by anywhere like this, based on the Gaussian distribution. Same way here. Okay, then you have another mountain like here. So if you cut like this, right? Okay, and then you look at the surface when you cut it. That looks like this, right? So this point is this point. That is a second point like this, S2. And since we cut it here, right? This one looks like two different mountains. Okay, that is Gaussian. So this is the what the symbol looks like when you transmit this one, and this is what the symbol. This is the probability density of the symbol that you receive when you transmit this symbol. What can happen is that even though you transmit this one, sometimes with a very low probability, that symbol is received somewhere here. So in this picture, right? So you transmit this one, but with a very low probability, sometimes it is received by somewhere here. If in that case, that will be detected by this symbol because that is closest one. So the receiver basically receives some symbol and make a detection, right? In this case, when you do detection, you basically cut the half like this, and every symbol that you receive on this right plane, you consider that as this one when you recover the transmit symbol, right? So that is going to be an error. So therefore, here on the blue shaded region and also red shaded region, these two regions are error. Okay, error case. Blue one is the error when you transmit it S1. Okay, and red region is the error case when you transmit it S2, but that is erroneously received by S1. Okay, so these two. And this one is called the false alarm, typically, and this one is a missing error probability. Okay, that's why we call it PM and PF. Typically, right? In fact, this is very basic, and this is we call as a hypothesis test. This is one hypothesis. This is the other hypothesis. Since we are talking about binary hypothesis, this hypothesis. Actually, this basic model, you'll see it a lot of places. when you talk about the binary transmission like BPSK, or some of you probably heard about cognitive radios, right? In cognitive radios, people start from this same hypothesis, same model, okay? They do the same way. They start from the same hypothesis like this. The thing is that here, I didn't make any assumption about S1 and S2 in this model. Right now, in case of antipodal signal, S1 is going to be minus energy, S2 is going to be positive energy. Okay, that's how I map it. Okay, because I assume that I use the antipodal signal. But if you look at the next picture, which is the orthogonal, then I show you the same hypothesis, similar hypothesis, and I draw a similar two Gaussian distributions, right? But in this case, S1 is 0, okay, 0, which means no energy. S2 is going to be some energy. So this is like on-off, right? On-off, right? On-off. Something like this. So these hypotheses can be used in the on-off like scenario, on-off binary. That's called the orthogonal, right? On-off. Whereas the previous one is antipodal, positive, negative, +1 or -1. So this kind of antipodal, the orthogonal or on-off binary transmission, you can still use the same hypothesis, and for cognitive radio system, you will see these kind of hypotheses. So the cognitive radio system, some of you probably heard about that. In that case, the goal, the fundamental goal, primary goal is try to detect some energy, try to find out whether there is some user or not. So if there is a certain user, then you will detect some energy. If there's no user, then no energy, right? So it's like this. From the receiver point of view, if you measure a certain, if you take some of the sensing, that's what we call as sensing. When you do sensing, then you will get some energy. You will measure some energy. If you have no energy measured, okay, that means this one. If you measure a certain energy, then that basically means this one, right? In terms of this model. So you can use the same model like this, okay, and try to find out what would be the error probability. The goal, even in that case, is that you want to minimize this error probability, okay? So something like this. Okay, I'm the receiver, say cognitive receiver, and I want to find out whether some transmitter is around me. Okay, that's what I like to find out. The only way that I can do is that I want to measure a certain energy. If there is a certain transmitter, he probably is transmitting something, right? So therefore, if I sense a certain spectrum, I can probably measure a certain energy. Okay, so just simply measuring certain energy, I can find out whether he is there or not. Okay, as simple as that. Energy measurement, energy detection. But however, what can happen is that when I do a measure, right, then I can measure a very little energy, such that I cannot make sure, I'm not 100% sure that whether he's there or not. If I receive a very strong energy, then I'm pretty sure that there's a transmitter. And if I measure almost a zero energy, then also I can say, looks like there's nothing. However, there's a certain energy, maybe small, tiny energy, whether I cannot really, decide whether he's there or not. You see what I'm saying? So there's a certain area, then I can make a misdetection or false alarm. What is a false alarm? False alarm basically means that there's nothing, but falsely I think that there is something there. That's a false alarm. So the false alarm probability basically means that there's nothing, in fact, but I consider that there is transmitter. That's a false alarm. Whereas missing basically means that actually there is. But for some reason, I was not able to detect anything, so falsely I consider that there's nothing. That is an even bigger problem. There is actually, but I think that, okay, there seems to be nothing. So there's a missing probability. That's a big problem. So the typically goal is to minimize these two. Okay, each one has its own problem. So we want to minimize both of them. Okay, so typically when you propose a system or when you design a system, your goal is to reduce the sum of these. Okay, this one can be modeled. In fact, look at F1. Just look at the blue curve, blue shaded region. This region can be calculated by Q function. That's exactly like this, right? So this is a blue region. That's a blue region. So since we are using the Gaussian distribution, this region, this area, can be simply calculated by Q function. So that's Q function. And this red one is also Q function. You just take a, mirror image, right? Then you will see that there's a red part right here. So that area, you can still use a Q function to calculate this. So both are Q functions, okay? And what we want to do is to minimize the sum of these two. That's typically the goal when you design a system. Okay, and this previous, the antipodal case, and the next one, the orthogonal case, it basically the same. Only the difference is that the distance between those two symbols is different. Okay, I don't care this is antipodal or orthogonal. Okay, that's none of my business in terms of a bit error rate. Okay, what I care is the distance between these two symbols. That's all I worry about. Okay, I'm not worrying about the actual shape. Okay, what matters is the distance between these two symbols. If I make the distance further away, that basically means that this Gaussian is going further away. Therefore, this region is going to be reduced. Okay, but typically, when you do the antipodal signal, we basically assume this one has the energy of square root of EB. This one also square root of EB. Therefore, when you take the average energy, right, then you square of that, then you square of these two, you flip that up and square the total average. The average energy is going to be EB. Okay, that's what I like to make sure. And if you go to the next one, orthogonal case, this one nothing, you have some energy like on off. Therefore, you square of that and average it out, then it's going to be again E of B, right? That's why I put it this way, okay? In order to make a same fair comparison, you want to make sure that the energy, average energy should be the same. That way you make a fair comparison. So that's why I introduced you these two things. But if you look at this way, look at the distance between these two symbols, distance. This distance is shorter than the previous antipodal case, okay? That really matters in terms of error rate calculation. So once you have a smaller distance, that basically means that here, inside the Q function, you have a distance, like right here, okay? This is the actual BER. Inside the Q function, you have a distance like this, okay? This is the function of distance. This D is in the numerator. So when you have a small d, that means you have a small value in here. Small value basically means that this one goes here, okay? This one goes this way. That means you have a larger area, meaning large errors, okay? Okay, this is a PDF. That's why I cannot show you the animation. But anyway, if you remember this animation, right? This animation basically, let me go back to the animation. Yeah, that animation basically shows you that QPSK can be split into 3 different binary transmissions, right? Suppose when you transmit this symbol, we are talking about only the error case, right? When you transmit this one, there are 3 different error cases. You transmit this one, but for some reason, that is received by somewhere here in this quadrant. Therefore, that is erroneously received by this point. That's error case 1, okay? In that case, as I said, the bit error rate is only function of D, this distance. Okay, so this is D, therefore you put the D into the Q function as we did before. This is the error. Second case is that you transmit this one, but erroneously, because of noise, sometimes you receive somewhere here. That it will be detected by this one, so therefore that's error case 2. In this case, again, you have the same distance, you will get the same error as before. Third case is that you transmit this one, but that is received by somewhere here. Okay, that's error case 3. But in this case, this D, in fact, is longer. It's larger than previous D. Therefore, your error rate, this error is a little bit lower than the previous 2. How can you see that? Is that you see you have a little bit, you have 2 ES, whereas the previous case is ES, right? When you have 2 ES, which means that the inside of Q function, this value is a little bit larger, bigger, right? That means in the Q function, that threshold goes further to the right, right? So therefore, the area for error is lower. Okay, so you consider that. But typically, when you consider high order modulation, like this one, right? This is QPSK, but you can even think about 16 QAM. Okay, high order modulation, you cannot really calculate one by one like this. There are so many different symbols. So it is typically you don't do that. What you do is that you use a bound. You don't want to calculate the exact one. Sometimes it is not possible. So therefore, no one pretty much try to find out the exact BER, which may not be possible. What people do is to use a bound. Okay, but among those many bounds, people use union bound. Union bound is like overestimating your BER. Okay, so in this case, we have 3 different things, right? Union bound basically means that the union of all these things. But when you do a union, what happens is that among these 3 different error cases, pick the one with the highest error. So in this case, these 2 have the same error, and the third one has a lower error. So therefore, these 2, the first these 2 have the bigger error. So you pick this one or this one, these are same, and then just multiply 3. Okay, that's the union bound. In this picture, what that basically means is, let's say you transmit this symbol and try to find out the closest one. Okay, why is the closest one? Because the closest symbol probably gives you the highest error, right? That's why you pick the smallest one and calculate the error, okay, between those 2, which gives you the highest error, highest binary error, and then multiply all the symbols, -1. Why do you do the -1? Because you want to subtract your own, right? We are multiplying only the number of error cases, which is going to be a total -1. Okay? So that's a union bound. The biggest error probability times number of error cases. As simple as that. That's the error bound. And you typically use error bound for all the higher order modulations. In fact, this is not part of the slide, but I want you to understand very clearly about the symbol error rate and bit error rate. What is the difference between the symbol error rate and bit error rate?
Symbol is the combination of bits.
Yes.
More bits in the symbol.
Okay, that's correct. But okay, let's pick an example. In case of QPSK, you know that one symbol contains 2 bits. So in terms of if you draw, let's say we want to draw a waterfall curve like a BER versus SNR. And also we also draw a SNR, the SER, symbol error rate versus SNR. How can you compare? Is it going to be same? For BPSK, both will be same, right? In fact, for BPSK, there's no symbol error rate. Yeah, you can say that, but these 2 are same because one symbol is 1 bit for BPSK. But in QPSK, one symbol has 2 bits in it, so therefore BER and SER is different. And you need to understand clearly about this. A lot of people confuse about, and they sometimes interchangeably use those things, so that's very wrong. So what is important is that when you talk about symbol error rate, okay, then for both the symbol error rate, bit error rate, that the error rate depends on the energy, right? Look at this one. This one, symbol error rate, is a Q function of symbol SNR. Because you see that ES, right? That's a symbol energy. We use always the same noise power. Noise power is the same regardless. Okay? This one is noise power and not, those also noise power and not. But in this case, in the symbol error rate, you see that we use a symbol error, symbol energy. Whereas in BER, we use bit energy. Okay? So what that means is your symbol energy and bit energy is different for higher order modulation. Now let's pick an example. Let's say we have one symbol, one QPSK symbol, and that one symbol has energy 1. Okay? In that case, E sub S equal to 1. Because we said that symbol energy is 1. So therefore, let's say ES, the symbol energy, let's say we make a symbol energy to be 1. Okay? Now, let's think about the bit energy. What is the bit energy for QPSK signal? In case of QPSK, the bit energy in this case is going to be half, right? Because we have one symbol. This is symbol. So the energy in this symbol is 1. But inside this symbol, we have 2 bits, right? So EB, bit energy, is just energy in the 1 bit. So therefore, it's going to be half. Because we have 2 bits, right? So therefore, when you calculate, let's say you calculate symbol error rate. Let's say symbol error rate versus SNR. Okay? In fact, SNR is a little bit confusing term. So let's say this is ES over NR. Okay? Once you use ES over NR, that basically means that I want to look at the symbol error rate. That's why I said ES right here, right? That means I want to see the symbol error rate. In that case, let's say we have this curve. Now I want to overlay another picture. And let's say in this case, I want to choose this one as EB over NR. Therefore, I want to see a BER. And I want to plot these two on the same picture. Okay, once I do that, then how does it appear? Typically, is this higher or this is higher? For the same, think about this one, right? Let's say we have 2 bits inside one symbol. 2 bits, let's say I transmitted 2 bits, 0, 0, okay, in one symbol, right? And when we think about the error cases, this may be received by 1, 0, or received by 1, 0, or received by 1, 1, right? In that case, this one is 1 bit error, but we have a symbol error because anyway, 1 bit error still the symbol error. This is 1 bit again. This is 2 bits error. So each of these is a 1 symbol error, but some cases it's going to be 2 bit error.
So symbol has to be larger than this.
Typically, symbol error is larger than bit error rate, right? Typically. So what you need to do, but how much? Just half. Think about this one as half. So therefore, I guess we should talk about this one. Okay, typically we say SNR. So what exactly mean as SNR? What is SNR? SNR, you know that it's a signal power divided by noise power, right? So what exactly means as signal power? Right here.
transmitted? What to-
Let's make it a little bit more detail. Okay. So here in the transmitter, typically you have a modulator. Definitely here you have a demodulator, right? Demod. And you get some here before you demod, you get a symbol. Okay? Here you start with the bits and you do the modulation to change to symbol. So this is where you do a QPSK encoding or modulation, right? And this is you do a demodulation. So once you do the modulation, you change bits to the symbol. Okay? Now right here, after the demod, after modulation, now you are transmitting complex value, one of these four, right? That's what you transmitted over there. And after you add some of the noise and also the fading channel, you receive another complex value. Okay? And then let's suppose that we only have a noise. Then you receive a certain complex value. In this case, let's say in the transmitter, you transmit this one. In the receive antenna, let's say you received some other point, maybe here, because of this noise, right? So after the noise, right here, you receive another complex value. And then what you do is the demodulation. What the demodulation does is that you try to find out, let's say you receive this point, then this quadrant, you basically detect this symbol as this one, right? So you basically make a detection. That's what you do in the demodulation, simply speaking, right? So once you do that, now you convert it back to the bits. Okay? So right here, you again came back to bits. Right here, it's bits. Here, symbol. Here again, symbol, it's bits here. Simply speaking, right? That's what it is. Now then, when we talk about SNR, we want to define clearly signal power. So what is signal power? Is this the power here, or is this the power here? Or what is it? That's exactly what I mean as symbol error rate and bit error rate. Typically, right? Typically, when we talk about SNR, we want to think about symbol power right here in the channel. Okay? That's what we typically use. So signal power typically is the power that's floating around in the air on the medium channel. That's what we define as signal power, unless otherwise you state. Okay? But some people, in some other cases, they interchangeably use it and try to define this one as this power. Okay? But the correct one, the correct way to define is that the energy right here in the bit, that's going to be EB. Okay? This one. The energy per bit, this is energy per bit. Energy per bit. That's EB. Whereas right here is energy per symbol. That's ES. Okay? So typically when you write it into the EB over N naught, we call this APNO, or ES over N naught, then it's pretty clear. Because from this one, now we understand that ES over N naught basically means the SNR right here. And EB over N naught basically means the SNR right here after demode. Okay? That's pretty clear, but a lot of people actually say that SNR. Now there's a confusion whether SNR means this one or this one. There's a little bit confusion when you say SNR, but when people say SNR, typically that means this one. Okay? Typically. Not always. Maybe some people just, use this one as SNR, like interchangeably, but that's not correct. Okay, but typically SNR means this one. So when you increase the SNR, make higher SNR, small SNR, that means this one. Okay, so in that case, I'd like to ask you one thing. Now I'd like to compare BPSK and QPSK. You know that when you typically use a higher modulation, you get higher error rate. Okay, typically that's the case. If you use, let's say, 16 QAM, you can even have a higher bit error rate. Higher bit error rate basically means bad, right? Okay, higher modulation typically means higher error. Okay, so now let's compare these two, BPSK and QPSK, and I want to see BER, bit error rate for these two. Okay, and I want to make this x-axis as M0. And let's say my BPSK like this. What happened to the QPSK BER?
Should be a little bit further than this.
Should be a little further than this, right? 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 No, that's incorrect. It's actually same. Why is it same?
Because the bits are the same.
Can you elaborate that? When I talk about BER, right, and when I want to see the APNO, then my point, I want to consider that I want to find out the BER with respect to EB. Okay, I fix the EB. Okay, I fix the EB. That's what I'm doing. That's what I'm trying to see, right? I fix the EB and trying to find out what will be the error probability. But look at the QPSK. In fact, this QPSK is exactly the same as two BPSK. One BPSK in this axis, the other BPSK on the y-axis. This is exactly the same as just two BPSK, right? How do you implement the QPSK? One axis, one BPSK, you modulate with the cosine, right? The other BPSK, you modulate with the sine. And you know cosine and sine are orthogonal. So they do not interfere each other. So it's exactly the same as you use two BPSK, two independent BPSK, right? So therefore, the error rate of one BPSK and the other BPSK, average sense, it should be the same. If you take the average, again, the total BER should be the same as BER, the BPSK, okay? So if you look at the BPSK, the BER, these two are same. If you look at the BER, okay, think about this EB is fixed. However, that actually gives us a little bit confusion, right? How come these two have the same error rate? Okay, the trick is that we fix the EB. That basically means that if you cut it here in the channel SNR, now in case QPSK, you are basically using a double SNR. Double channel SNR. Sometimes people say channel SNR, people say CNR, okay? You probably heard about CNR sometimes. That means channel noise rate, channel SNR, right here. Some people call this a CNR. But anyway, in QPSK case, we use a double SNR, double ES over N0. Why is that? Because I fixed the EB. In order to make a comparison like this way, I use let's say I use the EB in the BPSK, and I use the same EB for QPSK. That corresponds to a double SNR right here in case QPSK. You see what I'm saying? Let's think about it this way. In BPSK, I have a QPSK, right? I make one symbol in BPSK. Also, I make one symbol in QPSK, same size, same symbol. I'm basically assuming using a same sampling frequency. So the symbol looks exactly the same. However, inside the symbol, this one is 1 bit, this one we have 2 bits, right? That's QPSK. However, in order to compare the BER versus the EB over and not, what I do is that I fix the EB. Okay? This energy, since I have 1 bit in one symbol, this whole thing is EB. But in case of QPSK, there are 2 bits. But I fix the EB, so therefore this energy should be same as that energy. That's what I did, right? So therefore, in order to make the same energy per bit, I make a little bit bigger like this. So this area, the energy, should be same as this energy. Therefore, if you think about the energy in the symbol, now it's a double energy in one symbol. So therefore, right here in the channel, okay, you have a symbol, right? Right here, the symbol is flowing. Symbol is, flowing around. So therefore, if you think about the ES, at this point, the ES of QPSK signal is double the ES of BPSK right here. Okay? Is it confusing? So therefore, if you plot the BER versus the EB over and not, QPSK and BPSK are the same. However, if I plot the SER versus ES over and not, now I want to measure the symbol error rate with respect to ES. So therefore, what I do now is that I want to fix the ES. Okay? BPSK, EB is the same as ES. But in this case, I want to fix the ES, this amount. Right? Therefore, if I calculate the EB in QPSK case, now it's half of a BPSK EB. Right? But if I cut it here, I'm basically making a fair comparison because ES for both cases is the same. Okay? In that case, you will see this 3 dB difference. This SER. This is SER. Okay? So BPSK SER is right here. QPSK SER is right here. That is QPSK SER. So typically, QPSK has a higher bit error rate than BPSK only when you talk about SER versus ES or not. But what I'm saying is that would be the right way to compare. If you really focus on the EB over and not, that's okay. I mean, you can clearly state it and you can go ahead. In that case, both will be the same. Okay? However, however, in that case, we are talking about different SNR over the channel, right? QPSK has a double SNR in the channel. So, yeah.
I think that bit error rate in EB or not is not a realistic figure. For example, if you compare
Which one is not realistic? This one.
BER and EB or not. For this case, it's okay. But if you are going to compare QPSK and 16 QPSK, then it's getting more and more complicated. And how could you draw the line?
That's the same way. Let's think about 16 QAM, right? Same way. 16 QAM. 16 QAM, you make the same symbol like this. And in 16 QAM, you have 4 bits. So it's the same way. If you want to find out the BER versus EB over and not, then again, I fix the EB. Okay? So in that case, this EB should be same as this EB in order to make a fair comparison, in order to see the BER versus EB over and not. So therefore, I'm going to use the same EB over this one. So therefore, if you think about ES, since I fixed the EB, same as this one, ES for this guy is going to be 4 times ES of this guy, right? So same way. Same way. So in that case, it's not going to be same, in fact. It's not same, actually. Why is that? Even though you fix the QPSK is a very special case, okay? So therefore, if you think about BER versus EB over and not, BER of both things is the same because this is very special. Why is it special? That is special in the sense that we have two BPSK, and one is modulated with the cosine, the other is the sine. Therefore, these two are orthogonal. So the complete orthogonality is guaranteed for QPSK. This is a very special case. Whereas if you use 16 QAM, we can do the same way. I just fix the EB, okay? Same as the BPSK. I want to compare the EB, and I want to plot the BR versus EB over and not. Okay? EB over and not. Okay? In that case, 16 QAM, even though you fix the EB, 16 QAM BR is not going to be the same as BPSK. Why is that? Because this one has no such specialty. Okay, 16 QAM, we have 16 different symbols, right? So BR, even though you fix the EB and compare the BR for this guy is actually a little bit higher. Okay? But this is a very special case. But what I'm talking about here is that you need to clearly understand the symbol error rate and bit error rate. When you look at the BR and SER, you have to clearly define what would be the reference if you use EB or if you use ES. When you use ES, you get the different symbol error rate. You get EB, you get the very different. Okay? It's confusing, right? It's confusing, but think about it clearly. Think about that symbol error rate is very different from the bit error rate. I mean, symbol energy, ES, and is very different from EB, especially for high order modulation, right? So therefore, your error rate should be different. Okay? Any question? No? Okay, so I want you to look at it clearly. So far we've looked at the case error rate in case of AWGN, but even when you have a fading, you can use the same technique. But this one, we can look at it a bit more detailed right here in this plot. Okay, this was the case of BPSK and in AWGN channel. But when you have a fading channel like this, right? Then from this model, as you see that now symbol S is multiplied by H because now we have a fading channel. When you have a fading channel, then what happened? Okay, what happened is what I'm showing you here in the previous plot. Okay, let's see here. When you have a noise only, right? Then you transmitted one of these two symbols, and that is added with the noise, and you receive some other points. Okay, but when you have a fading, now what happened is because of this fading, which is multiplied to the symbol, when you transmitted these two symbols, that is multiplied with H. In that case, it can go anywhere depending on actual H, value of H. This one can go anywhere. In this case, in this particular example, H is multiplied such that this symbol now goes to this symbol. This is just one example. Okay? And then you add the noise on top of it. So it's going some other points like this. But now what happens is H, this H, right? This fading H follows a fading channel statistics. For example, Rayleigh channel. Okay? So what is a Rayleigh channel? Rayleigh channel basically has this amplitude PDF, right? So therefore, when you go through the fading or Rayleigh fading channel, typically this one is getting reduced with a certain high probability. Okay? But anyway, so this H is multiplied, and this H actually is a time varying, and it's random. So therefore, when you transmit this symbol, now sometimes, depending on the H value, it's getting smaller. If you're getting smaller, that means this distance is getting smaller. Some other times, if you're lucky, then H is multiplied, big H value is multiplied, therefore the distance is getting further away. But it's random. So therefore, if you take all the average out, then you will see this kind of calculation. Okay, this is gamma, right? Gamma is the SNR, and this Q function of square root of 2 gamma, that's gonna be the AWGN, the BR in AWGN, BPSK BR in AWGN. Okay, that's the case where there's no fading, only noise, Gaussian noise. But since we have a fading, right? Sometimes the distance is getting further away, sometimes getting smaller, the distance getting smaller. But in terms of statistics, you multiply the PDF of the gamma, right? So what that means is if the SNR is bigger, it's a big SNR, that means what? That means the distance is getting further away. So you have a lower error. But sometimes the SNR is lower, that means you have a higher error, instantaneous error, higher error. So therefore, you average it out like this, right? So basically, you're taking average out like this. Sometimes this F, the gamma, is high, sometimes low, right? And that PDF basically shows you the probability of each gamma, each value, right? And you average it out like that. That's going to be the average bit error rate when you have a fading channel. This one basically shows you that when you have multiple antennas, then as I showed you earlier, now the PDF, this PDF, as long as you use a BPSK, okay, it doesn't matter how many antennas you use. As long as you use a BPSK like this, you get the same Q function. Okay, what is different based on these two receiver antenna is going to be this PDF. This F gamma, this PDF is now different when you use 2 antennas, 3 antennas, depending on what receiver you use, how to combine those systems, okay, how you define the system, that matters, that actually make this F gamma to be different, okay, but this Q function depends on only the modulation. And this picture basically show you how to think about the QAM modulation. Okay, QAM modulation is like this, right? This is the case of 16 QAM. You have 16 points. First of all, let's think about some basic about QAM modulation. Compared to QPSK modulation like this, right? We have 4 points. What would be the benefit of the 16 QAM? Simply speaking, the benefit that you can get out of this 16 QAM is that you can transmit more bits, simply speaking, right? That basically means it's a higher spectral efficiency. Okay, that's the little bit, how do I say, advanced way to call it. Okay, so you want to call that as a higher spectral efficiency. When you use higher modulation, we can have higher spectral efficiency. Okay. However, that's not free, right? You have to think about some expense.
The trade-off.
Huh?
The trade-off.
Yeah, but when you compare the QPSK with this, right? Now think about the QPSK. QPSK 4 symbols are on the unit circle. What does that mean? Huh? Yeah, in the constellation, 4 symbols are on the unit circle. Okay, whether it's on the unit circle or outside the circle, that basically means energy, exactly, energy. Okay, when you have 4 symbols on the unit circle, that means every symbol have the same energy because it's on the same radius, right? Same energy per symbol. However, in this case, right, definitely those are not on the unit circle. In fact, the unit circle is somewhere like this. So some of them are inside, some of them are outside the unit circle. So what that means is when we use a QM QAM or 16 QAM, now depending on which symbol you transmit, the symbol energy is is different. Sometimes you get a small symbol energy, some other times your symbol energy is big. Okay? Now symbol energy is varying. Okay? Why does it matter? What's wrong about that? When you design a system, right? These symbols eventually go out through the antenna, right? Right here, I just make a very simple block diagram. So when you do the modulation, you get a symbol. This symbol looks like it just go out through the antenna. But what is actually happening is that before you go through the antenna, since we are talking about baseband processing right here, baseband should go to the carrier, right? So when you go to the carrier, there will be RF circuits. Inside RF circuit, there are a lot of blocks, but one of them, most of them, the most important thing is the mixer. Okay, what is mixer? You multiply the carrier frequency in order to modulate, right? That's the mixer. And the second thing, of course, when you multiply the mixer, you have to have filters, right? Because when you multiply certain frequency, now think about that. When you multiply cosine, there was originally was cosine, and you multiply cosine, there will be harmonics. You multiply F0, FC, let's say FC is a carrier. When you multiply the FC, you will mathematically you will make FC, 2FC, you have harmonics. So you have to cut off the harmonic by filter. Okay, you should have filter whenever you have mixer. But what I'm saying is that after that, after the mixer, what you need to have is the power amplifier. Because you have to transmit, right? Transmission requires a lot of power. You have to do amplifier. Okay? Power amplifier. When you do the power amplifier, typically power amplifier, such a device is not linear device. What does that mean? What does it mean by linear or non-linear in this case? What it means is that what is a power amplifier? Typically, power amplifier works, simply speaking, works like this. Like this, simply speaking. You have some power in baseband that is amplified. Let's say this is 1. Is amplified, and the output of the power amplifier is going to be 10. I'm just giving you an example. Okay? And if I have a 2 in the baseband, that's going to be 20. If I have the energy 3, that corresponds to the 30 at the output of the power amplifier. Okay, that means linear. However, in the power amplifier, typically the device has a limitation such that this linear region is limited. It's not linear forever. Okay, such a linear region is pretty narrow, maybe only from here, and from here somewhere it's going like this. So if you have some high power, it's no longer 40, it's less than 40. That makes a distortion of your signal. That such a distortion will be received very differently. Therefore, you have a very high error in that case, right? So typically, you change the error or energy in the baseband is not a good one. Okay? The best way is you make sure that you have the same energy every time. That way, you make sure that that energy is inside the linear region. That's the best one. Okay? If you have to change the symbol energy, then you want to minimize the range. Okay? If you have a wide variation in the energy right here, here you have a power amplifier, and you have to minimize the swing range right here before the power amplifier. If you have sometimes too much energy, sometimes too low energy for power amplifier, that basically means that power amplifier has only this of linearity range, but your input is going to be swing like this. That means your output will be distorted. That's bad. What I'm talking about is the practical problem that you will see in the any wireless system, because any wireless system has to have a power amplifier, right? So because of this problem, in typically OFDM, what problem do you see? Peak to average power, peak to PAPR, peak to average power ratio problem. Have you heard that? Have you heard PAPR problem? Yeah, in OFDM you have a PAPR problem, and this is the problem because of this. We have limited linearity in this device, but in OFDM, since you use the DFT and IFFT, therefore you do a lot of multiplication addition inside the FFT when you go from time domain to frequency domain or vice versa. So therefore your input to the PA has a lot of swing, a lot of power energy difference per symbol. So therefore you have this problem. So therefore I'm saying right here is that typically when you change the energy for different symbol, that's not a good one. Okay, that's somehow overload or overhead for the power amplifier or some other devices. Okay, so that's a little bit bad side. However, since this one has a higher spectral efficiency, these days a lot of systems use this one. Okay, so this is very popular, even with this, some bad side. Still, this is very popular. And this picture basically shows you how to analyze the BER when you use this modulation. If you use this 16-QAM modulation, how can you analyze the bit error rate? Okay, that's what I'm showing here. To do that, we want to understand this one first. When I say QPSK, I said that QPSK is just as simple as 2 BPSK, right? So one BPSK on the y-axis, the other BPSK on the x-axis. Simple as that, right? This 16-QAM, same, okay? I'm using in this case, right, in 16-QAM case, I'm using 4 PAM, pulse amplitude modulation in one axis. I'm using the other pulse amplitude modulation. So this one is same as I'm using 2 pulse amplitude modulation. Okay? Same way as a QPSK. Similar way. So therefore, in order to analyze the BER for this modulation, QAM modulation, we need to first understand the pulse amplitude modulation. This is the case of 4 pulse amplitude modulation. Okay? Once we understand this one, then 16-QAM is just the same as the 2 of these. Okay? So it's simple. So this one this one is not binary anymore, right? Because we have 4 symbols. BPSK was 2 symbol, binary was 2, but we have 4. And pulse amplitude modulation is such that each symbol has a different amplitude, right? So in terms of voltage, it's like this one corresponds to, for example, corresponds to like -5 volt, -3 volts, -1 volt, 1 volt, 3 volts, something like this, right? If you think about this one as voltage. Voltage is like amplitude. So each one has a different amplitude. Okay? Think about the antipodal BPSK, antipodal modulation. We had 2 symbols. It was -1 and +1, right? That was the case of antipodal. This is a kind of extension. We have not just the 1 and -1, we also have a 3 and -3. That's the case for pulse amplitude. Emory. What is Emory? This is not Mary, not the name, right? Emory. If M is 2, that means binary. Okay, that's Emory, right? Yeah, I know that everyone knows that. But the M is 4 in this case, so we have 4. In this case, we have to separate these to 2 different cases. One case is inner points, and second case is the outer points. And we have only 2 outer points, right? This one and this one. Even though M is like 16, still we have only 2 outer points and 14 inner points, right? These outer points, we have only the 1 error case. Okay? This is what we transmit. And when you have a noise on top of it, if you have a noise and this one is received by further away like this, still okay. Because all these region is considered as this one. So if you have an error in this area, in this direction, that's okay. It's not an error. Okay? This point is going to be only error when we have noise and that is received by somewhere here. Okay? Only this one is going to be considered as error. So this point and this point, we have only one error case, like this. Right? Only one error case for outer points. However, for inner points, this one can be, this one have two error cases, right? So therefore, we separate out inner points and outer points. And as you see here, the inner points have two error cases, so therefore it has a double error. So as you see here, the PS2, the S2 inner points, S3, these inner points have this error probability. How to find out this one is like this. So for S2, right? For example, if you transmit S2, S2 can be received by S1 or S3, which are the error cases. The error probability for each case is like this one. Again, it's a Q function. So that if you add these two together, that's going to be this one. We have a 2 right here, right? Because we have two error cases. However, for outer points, now we know that this is half of this. Here we have 2, but here we have 1. So this one is the error for outer case, outer points, these two. Okay, once we have this, now we are going to add it like this. The reason that I'm using m and m minus 2 divided by m is because that in general, when you have m, in this case, this is an example when m equal to 4, but m can be anything, any value. So when you generalize it, and m can be any value, then m minus 2 is the number of inner points, because we have only 2 outer points. So 2 goes to here. So that's the error probability for outer points. This is for inner points. You add it together, that's the total value, total error probability. Okay? So this is the error probability when you use this amplitude, pulse memory, PAM, and QAM, 16 QAM is nothing but use just 2 of the 4 PAM in parallel. So therefore, if you look at this one, that is actually just double of the previous one. Okay? So that's how you calculate the amplitude, the BER error rate of QAM. This one basically shows you some very popular approximation. Here again, it's an approximation, right? Meaning that this is not accurate. But we don't care. Why? Because if you calculate the accurate error probability, that's almost impossible. So no one is trying to pretty much calculate the accurate one. This one, even though it's approximation, it actually still is very close to the actual value. Okay? So for we engineers, we probably put the value, more value onto the finding trying to find some bit error rate, even though that is an approximation. If that is still very close, then we want to make a simple one. If the exact one is like 3 different lines of equation, we don't like that. We are not a mathematician, right? We don't like such a complex mathematics. We want the simple one as long as this one is close enough. Okay? So this one actually approximates very closely. So therefore, we use this one. In this case, it's very simple as just one Q function, but we have alpha and beta as a coefficient. And this actual value of alpha beta depends on your modulation. So these are the example. When you use BPSK, for example, then A becomes 1 and beta becomes 2, like this. Okay? When you use other modulation, you use differently. Here, actually, this plot, look at here. BPSK has no symbol error rate. This is a symbol error rate, right? This column is symbol error rate. This column is bit error rate. So BPSK binary, we have no symbol error rate. For QPSK, we have symbol error rate, we have a bit error rate. As you see here, the bit error rate of BPSK and QPSK are same. Okay? As I said earlier. Okay? And for other modulation, you can use this one, for example, as alpha and this one as a beta. Okay? So this is you can see this table in a book. So whenever you use some modulation, for example, M-QAM modulation, you can just simply refer to this book and just try to use this equation. Simply, right? You don't have to calculate all these things. We also talked about this one earlier. Now, when you use multiple antennas, for example, in the receiver, then there are several different ways to run the receiver. And if you use MRC, that means you basically combine all this SNR. Okay, that's what you can achieve. So the output SNR basically means the SNR right here after the combining. Then after combining, what you receive is the gamma 1 to gamma m, addition of all these things. What that means is you are basically adding all these SNRs. Okay? And once you have that, now we can consider each of them as the random variable, continuous random variable, and additional random variable corresponds to the convolution of all the PDFs. Okay? Convolution of all the PDF basically corresponds to the multiplication of let's say Laplace transform of each of them. And Laplace transform of this PDF is going to be MGF, which we covered last week, right? So what that basically means is, in terms of SNR, when you use MRC, right? SNR is just addition. Just add all the SNR. That's going to be your output SNR. That basically means the convolution of all the PDF. That basically means the multiplication of all the MGF. Okay, all these things are same. And once you do that, once you do this convolution of all these PDF, and each PDF follows a Rayleigh distribution like this, then the output PDF is going to be like this. And that's the solution of that. And we're going to talk briefly about this one a little bit later. And that's the performance. And when you have a selection combining, again, you change this one, right? You change how to operate the receiver. And earlier it was the MRC combining. In this case, I use a selection combining. So depending on how you operate the receiver, your output SNR is going to be different. And this is an example of selection combining. And mathematically, selection combining can be written this way. I'm trying to use the maximum one. Okay? Only one, but the maximum. From this one to this one, now we are solving the mathematical problem. So each one is now considered as random variable. I'm choosing the maximum one. That corresponds to the CDF of this way. Okay? And you make a further calculation like this one. So that's the how to find out the BER of selection combining, and this is the performance. So now, today what I'm gonna show you is some of the basic background and just try to help you to do research. Now I'm trying to show you some example of what we can do and what kind of research we can do for the performance analysis and such things. So first of all, since we are talking about performance analysis, what does it mean exactly by performance? This is the case of MIMO system because that's a little bit easier to show you. But any system basically is the same. This is just an example of MIMO systems. When you talk about performance, we have to define the performance metric. There can be many different performance metrics. The most popular one would be the error rate and capacity. There are some other things. When you look at some research papers, right? There are some papers which are trying to minimize the error rate. Okay? Or there are some other research papers that are designed to increase the capacity. But there are also some other type of research papers which are trying to minimize the complexity. Okay? Complexity can be another metric you can use. But here, the catch is that when you talk about complexity, right, then you have to think about that you cannot just simply reduce the complexity. The reduced complexity is typically good, but when you try to reduce the complexity, you have to make sure that your performance is not reduced. Okay? You should not sacrifice your performance and therefore you reduce the complexity, right? So given the same performance, you try to reduce the complexity. Okay? But anyway, complexity is another one, but typically we use these two as a performance metric. Error rate, as this example show you, this is the case where you run the MIMO system with the diversity mode. Okay? This diversity mode, if you remember, can be illustrated as a one thicker pipe. One pipe, but that's a thicker, more reliable pipe. Okay? Because we can achieve the diversity gain, so therefore this pipe can be thicker or more reliable. And more reliable basically means that you have a less error rate. So in this case, let's say I want to design a system like this. Then what would be the goal? If you think about this arrow, right? This arrow basically shows you the amount of water you deliver. You don't want to measure the amount of water you deliver in this case, right? Okay, that's capacity, right? How much water I can deliver from the transmitter to receiver. That's same as the data rate, same as capacity, and you should not use the capacity as the performance metric in this case, right? If you want to use capacity as a performance metric, in other words, if you want to increase the capacity, you should not use this way. You should use this way then, right? So if you choose this way, this mode, that basically means that now your focus is try to minimize the bit error rate, because that's why you choose this mode, okay? And this one, you want to minimize this error rate. That should be your focus in this system. Okay? And the second system is that, suppose in this MIMO you use a spatial multiplexing, so therefore you make a two independent pipe. In this case, typically your focus is try to increase the capacity. You are trying to deliver much more water. Okay, that should be your focus, rather than minimizing the error. Of course, the best solution is that increase the capacity at the same time you reduce the error rate. That's going to be the best solution. But I'm saying that typically you choose only one as your goal. Okay? The goal in this case is try to increase the capacity. The goal in this case is try to reduce the error rate. Okay? This is your system basically. This is just illustration. This is your system. And how to operate this system depends on you. It's up to you, right? You can choose this way or you can choose this way, right? When you choose this way, then you need to focus to reduce the error. When you choose this way, you want to focus more on the increasing the capacity. Okay? So these two are the popular performance metric for any system. First of all, we want to study a little bit on the fading channel. This is the most popular fading channel, as you know. It's called the relay. And you can look at the PDF of this fading channel for amplitude and also SNR. So here is if you Google it, Google the relay, then you will see a Wikipedia page. Okay? That Wikipedia page basically introduces you this PDF. In fact, this PDF is the relay distribution for amplitude. And this is the picture, PDF and CDF. Okay? So this one is the PDF of the amplitude for relay distribution. Sometimes this is useful when you talk about amplitude, but for us, if we want to analyze the performance, okay, when we look at the performance, bit error rate, and all these things, bit error rate is a function of SNR. It's not a function of amplitude. So typically, we don't use this one. Okay, it is very rare to use this distribution. Okay, because we always use SNR for performance. So therefore, we use this PDF most of the time. When we talk about relay, we use this one. This is the PDF of the SNR. And you know SNR is a power ratio, right? Signal power divided by noise power. So this is a power ratio. Therefore, it's a square of amplitude, right? So when you have random variable x, which follows a Rayleigh distribution like this, right? This PDF. Then if you define another random variable y equal to x squared, okay? This is the PDF of x random variable. And this is the PDF of random variable y, and y equal to x squared. Then you see that the y follows the exponential distribution. We talked about this one earlier, right? Yeah, so this one actually is an exponential distribution, okay? But this is Rayleigh fading channel, and this is a PDF of SNR. And many other times we also use MGF, okay? And this one is MGF. And how to get this one? Laplace transform of this, and just change the sign of S, okay? That would be this one. So if you take the Laplace transform of this, that's going to be this one as a minus S. Sometimes you also see this kind of fading, okay? This called as Nakagami fading channel. Sometimes you see this channel. This is a more generalized channel. Earlier in the Rayleigh fading channel, you have only one parameter, right? Go back to the Rayleigh. You have only one, alpha, sigma in this case. You have only one parameter. And if you use the PDF of SNR, here again you have only one parameter. That's going to be this one. What is this one, by the way? Gamma over bar, that means average SNR, okay? So this one is the only parameter that you need, average SNR. However, in the Nakagami fading channel, this is a more generalized channel. Therefore, you need two parameters, M and sigma. Two parameters, okay? So this picture basically shows you the PDF of amplitude, this one. This one is as you show here. In fact, in this plot, I copied this one from Wikipedia. And in fact, I found a mistake in Wikipedia. They showed M and sigma in this equation, but in the picture they use mu and omega. And it's the same as, mu is the same as M, and omega is the same as sigma. They have a mistakes like this. But anyway, so when this M is 1, let's say you put the 1 here. 1, 1, 1, 1, 1. Now then this becomes Rayleigh. Okay, when M equal to 1, the blue one, this blue, then this blue curve is exactly the same as a Rayleigh PDF. Okay, so therefore this one includes Rayleigh. However, when M becomes different value, now this PDF becomes different. So now let's see, when you have 0.5, M equal to 0.5, that's going to be black one. And this black means this black looks like what? It looks like a Gaussian distribution, but it's just half Gaussian, right? This is 0. So you think about the negative value, that looks Gaussian, right? This is just half Gaussian. And this half Gaussian channel is the worst channel you can ever see. Okay, so this model basically includes all different types of channel. This Gaussian channel, when M equal to 0.5, that's going to be very, very worst channel. Okay? And when you have a higher M, say M equal to 2, M equal to 3, now you see that the shape becomes red, yellow, and purple. Now the average goes to further to the right, right? That basically means it's more favorable channel. What does it mean by favorable channel? Less fading, okay? You have a deep fading, that is a bad channel. You have a very small fading, that's favorable channel, okay? So when M equal to higher value in here, right? Then this channel, this generalized model now is changed to another type of fading which has a favorable characteristic, okay? That's why we call this one as a generalized fading channel. We can convert this one into a worse channel like a Gaussian, or you can change this one to Rayleigh sometimes, or you can make this one as some other favorable channel depending on M. Okay? But this one is a PDF of amplitude. This is the case of PDF of SNR, and we always use this one. Okay, this one. This one again is has two parameters, m and gamma bar. Okay, m is called the fading parameter because we changed m. It actually results in a different channel statistics. This is MGF. Okay, you Laplace transform this. That's gonna be this one with the minus s. Okay, now we want to briefly talk about capacity. As I said earlier, the popular performance metric would be capacity and the bit error rate. So first, let's look at the capacity. We start from the basic, like in case of 8WGN, we use this capacity, right? This equation is from Shannon, right? We call that the Shannon capacity. So it's like log 2 1 plus SNR. This is SNR because P is the transmit power divided by noise power. So that's going to be SNR. And you know that the capacity typically has a unit of bits per second per hertz, right? You want to remember this. This is typically the unit for the capacity. Bits per second per unit, per hertz. Okay? For 8WGN, you have this capacity based on the Shannon capacity. Now, let's think about a system where you have some fading. Okay? Now you have fading. This is the case only with the 8WGN, but now let's think about the fading. Okay? We have transmitter and receiver. We have a fading channel. But CSI, channel state information, is only at the receiver. Okay? Receiver anyway knows the channel state information. So we are talking about some general type. So in that case, receiver knows H, receiver knows the fading, right? Then that's what I mean by CSI is available at the receiver. So therefore, from the receiver perspective, P is a transmitted power, H is what you experience over the channel. The square of that, that's the channel power. So you multiply that, that's the received SNR. Okay, that's received SNR. However, what can happen is that H is random. Channel is fading, so it changes over time. H changes over time, right? So therefore, you have to have an average out for this. So this one is average capacity at the receiver. Okay, so this is the received SNR, and H basically changes over time. So you multiply the statistic PDF of that and average it out. That's the average capacity at the receiver. Now let's make another assumption. Let's suppose that this channel state information, CSI, in other words H, is also known at the transmitter. Then what can you do? Now H is known at the transmitter also. Then what can you do? Okay. Let me give you a simple picture right here.
You can mitigate it from the transmitter.
How can you do it? How can you do it?
The MIMO techniques you use.
We are not talking about MIMO right here. I'm talking about a single case, right? I didn't make any assumption like that. Okay, so let's think about this one. In fact, that's pretty close. So let's think about this one. Single antenna. We have H, right? And if you look at this H in time domain, H changes like this, right? That's H. Okay, it's a time. Now, let's say transmitter knows H. Okay? What you can do is that based on this H, sometimes you have a lower channel gain, sometimes higher channel gain, sometimes very low channel gain. And this guy, the transmitter, knows this. Then what can this guy does is that I can assign a different power. What you always assume is that this guy used the same power, always. That's the assumption. In fact, that assumption is correct in case of this one, because the transmitter knows nothing. So transmitter just assign the same power always, all the time. But in this case, if the H, this guy, transmitter knows H, then this guy may want to change its transmitted power, right? Assign a different power. So now let's assign different power. Like this, right? like this. So what I'm doing is called the channel inversion. Okay? When you have a deep fading, I'm going to assign a big power. Okay? When I have a small channel gain, I have a big power. When I have a high channel gain, then I assign a small power. Okay? So this is this picture, the yellow one. Let's talk about the how much power I assigned. Okay? But that is inversion of the channel. You see what I'm saying? So therefore, what happened is, think about the model. What I'm doing is this, right? This is my transmit power that's multiplied with H. And H, it looks like this, right? This is H. And I'm trying to change the power of X. Then when you multiply these two, that's going to be like this, right? That's the motivation, and that's why we want to do the channel inversion. Okay? That's one way to do it. If this guy knows it. But this one sounds okay, sounds good, but this is not really practical, first of all. And this may not be possible at sometimes because there are several reasons. One of the reasons is that sometimes the fading is very deep fading. In that case, your power has to be like this big. That is not easy to do it. Okay, that's one of the problems. So therefore, some people actually assumes that generally we use a channel inversion, but in such case we clip it here. So it's like a capped limited channel inversion, and people, propose such things. But anyway, that is the basic one of the approaches you can do. Okay, channel inversion. Okay, but the main thing about channel inversion is that you can change the transmitted power right here because you know H. But this one is only true when you have a slow fading. What is slow fading? This fading is pretty slow such that you can follow. Okay, you can keep track of this variation. This is only true in that case. Now what happened in the fast fading? In case of fast fading, what that means is now this fading changes very fast, like this. So simply you cannot follow. Okay? You cannot follow and assign a different channel inversion, different power. Okay? This is very difficult to do it. In that case, what you can try to do is water filling. What was water filling? Remember we talked about this one, water filling? Huh?
You're making stick and then filling
Yeah.
power less and higher.
Yeah, at that time we talk about water filling in terms of a different spatial channel, right? Different pipe. Remember that? You can use the same. This is, by the way, the mathematical tool. Okay, water filling is not just for MIMO. You can use water filling for any other system. Now let's think about fast fading. Let's say this is my fast fading. Okay. In case of fast fading, I cannot keep track. So what you can do is that maybe you can take some of the duration, maybe from here to here. Okay. Each one is very fast, but I can take a certain time duration and I measure the average power. In other words, you want to find out the water level. Okay? And put the water level, for example, like this. Okay? And then you fill the water. This one is fill the water. In fact, let me change the water level. I make this water level. Okay, then this is my water. I'm just filling the water like this, right? Once you do that, now you see that based on this, you are using the different power, right, for each instant. So you can try to do the water filling in that case. Okay, so in the fast fading, what I'm saying is that you cannot really follow an instantaneous one. So therefore, what you can do is that based on the water filling principle, you can calculate this one. This one, if you look at it, by the way, what is this one? the bracket superscript plus. What does that mean? That notation is popular in the water filling. This one basically means that, let's say this is A, that means that if the A value is higher than 0, that means the output of this is A. If A is lower than 0 or negative, then you get 0. Okay, so you take only the positive value. Okay, you take the value of A in case of only positive. If the A is negative, then you just make it 0. Okay, that's what that means. Okay, so here, in this case, what the basic means is you calculate the inside here, and the value inside is positive, then that's the output. You get that value here. But inside this one, when you calculate the inside this value is going to be negative, then this value is going to be 0. Okay, that's what they mean. The details of this water filling, probably in a couple of weeks later, we're going to talk about it. And I'm thinking that maybe we can do some homework about these things sometime later, because this one needs a little bit of practice in order to understand clearly. Okay, and this lambda right here, lambda is the water level. Okay, and water level is calculated this way. Okay, whatever it means, lambda is from this way. So okay, we can talk some more detail later. Okay, this is a review of the slide from previous lecture. So we talked the alternative Q function last week, and simply speaking, this is the alternative Q function, right? The Q function has the original definition of this, but instead of doing this, we want to use this one, okay? Which has the fixed limit fixed lower limit and upper limit. Therefore, this is much better for us to do analysis. So this is called the alternative Q function. And this one, again, is MGF, which we talked about last week. And remember that this is the definition of MGF. We have a PDF for any PDF, right? This is just definition, mathematical definition. So you can bring any PDF and take the exponential S gamma, then that's going to be MGF. And when you look at this one looks exactly the same as Laplace transform, except S is minus S. So therefore, when you take actually a Laplace transform of this, that's going to be MGF with the minus S, okay? So that's the relationship between this one. So what that basically means is when you have a certain PDF, you don't actually have to mathematically calculate this integration by your hand. You can just look up the Laplace transform table and just substitute S to the minus S. That will give you MGF, right? Just look up Laplace transform table. And this is the example when you have F gamma as a Rayleigh, this is going to be MGF. In case of Nakagami, use this PDF here, then you get this one, okay? Okay, this one basically shows you one example of average error rate. Some of these things we covered last week, but let me do it again here. So this is one of the example that we do the bit error rate. Alpha, Q function, beta, gamma, this is the general like approximation of error rate, bit error rate, and also symbol error rate. And use your own PDF, and multiply it and average out over this PDF. Okay, that's typically how you do it. But this Q function can be replaced into this one using the alternative Q function, right? For some reason, I skipped the alpha. Looks like there's some mistake. So alpha is gone here. Okay, there was a mistake. But anyway, alpha was here. Okay, I'll make a correction. Then now you switch these two integrals. So in this first integral now go inside and bring this d gamma here, okay? And you calculate this one first, but this one happens to be MGF, so therefore this one can be now converted into this way. So this way basically means that as long as we know the MGF, then we can simply calculate that. So far, we haven't assumed anything. We didn't assume F gamma. Okay? This can be simply Rayleigh, or this can be Nakagami, or this can be the PDF of MRC. This can be anything. We didn't make any assumption. And this one, we also didn't make any assumption. This one, depending on the alpha and beta values, this one can be 16 QAM or BPSK, anything. Okay? So this one is pretty simple to do it. And with this equation, you can pretty much calculate the bit error rate for any modulation with any system. As an example, if we use a Rayleigh, then we know that the MGF is this one. So put this one into here, right? Bring this one, because this is S, right? This whole thing is S. Put this one in here to S. Then you get this one. Then you get this one, actually. You get this one. No, solution of this one is going to be this way. And how to do that? That I'll show you the next week, next slide. Okay? In case of Nakagami, use this MGF. Then similar way, we get this one. That ends up being this one. I'm sorry, this is another mistake, right? This is just simple copy and paste. Looks like this is not correct. Okay, I'll show you the correct one here. This is correct, but this is different. Okay, this is another mistake. But look at this one. Now, what I'm trying to tell you is that this is our final goal, this integration. You want to make yourself to be familiar with this kind of equation, like 0 to pi over 2, and you have a sine square plus something sine square divided by d phi. Okay, that is one type of integral equation. And once you reach here, that's the end. And this one looks pretty similar, but this one is a power to the m, right? This is another term. Then now, I want to show you why I'm saying that this is the target. Because once you reach such a target, then you can refer to this book. This is a very thick book. It's like 900 pages. This book basically shows you, and this book actually, they calculate all these different integration and show you exactly the closed form equation. Okay? And if you look at this book, there is some mathematical derivation how to do that. But in summary, simply speaking, when you do this calculation, that's going to be this one. When you do this calculation, that's going to be this one. That's all in the book. So no one wants to, you don't really want to do this calculation by your hand. It has no meaning. Okay? Once you reach there, then look at this book, refer to this book, and find out this equation, and use your own C, put that here. That will be the solution. Similarly, here, if you reach this kind of integral equation, then look at that book, find out this equation, and bring your own C and N into here, 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 right? That's going to be your solution. Okay? No one really calculate this one by hand. So that's why I'm saying this is going to be, once you reach that, that's it. You just use this equation. Similarly, for this type of integral equation, you can also find the closed form equations for each of them. However, for these things, it's pretty complex. So that's why I didn't put that here. But look at this book, you will find the closed form for each of them. Okay? So you don't really want to calculate all these things. That's what this is for, right? That's why we have such a reference. Okay, this is another example of MRC, which I showed you last week. So in case of MRC, when you use MRC, you know that this is the PDF. So we start from a general equation like this. And for this PDF, you use this one, because this is the PDF for MRC. So bring that one here, and you do some, and using the alternative Q function, you replace this Q function into this way, and switch that integral, and do the same way. Then you end up getting this one, right? Once you end up getting this one, that this equation looks almost same as my second equation like this, right? So therefore, I just simply look at this one and use my M and C. My C is this one, and my M, small m, was capital M. So use capital M and small this one in the equation, then I get the solution like this. Okay, next two slides, I'm trying to introduce you what kind of research we can do for these systems, for any this kind of system. Okay, I'm trying to give you some idea what we can do and what people have done. As I said, for performance, there are two different performance metrics. One is capacity and the other is speed error rate. When people try to look at capacity as a performance metric, people are trying to do this way. Typically, we categorize into two different cases. First is a CSI is known only at the receiver. Second is CSI is also known at both of them, both at the transmitter and receiver. When you assume this way, when you assume that CSI is only available at the receiver, then there's nothing you can do at the transmitter because transmitter knows nothing. So you are focusing more on the receiver side. And what you can do, especially for MIMO, is that some people use this one as their research topic. A lot of people actually have done this and they are doing it. MIMO receiver design. Okay? When people, maybe you want to meet some other graduate student, some other research scientist at the conference, let's say. And you start to have a casual conversation and try to talk about, let's say, oh, what's your research topic? You know, that's kind of basic way to ask a question, right? Introduce yourself and talk some of the research. And they say, okay, I'm doing a research on the MIMO receiver design. What does that mean? You definitely should be understanding, oh, okay, that means this, this, this. You need to understand what that means, right? A lot of people actually do this. So when people say MIMO receiver design as a research topic, that means that part of that is equalization. What is equalization? We covered that in some of the previous lecture, right? When we say equalization, that basically means that there is some interference. There is some interference, therefore you use equalization. What is interference in this case? Since we are talking about MIMO, what type of interference we are talking about? There are so many different interference types. What is interference type in this case? Let's think about very basic system, 2x2 MIMO. Interference that I'm talking about in case of MIMO is the inter-channel interference or co-channel interference. Some people call it as a co-channel. What that means is what I'm transmitting from the first antenna is received by first receive antenna. And if I transmit the symbol from the second antenna, that is only received by second receive antenna. That means no interference, right? This one only goes to this. This one only goes to this. That means no cross term, no interference. But this is definitely not the case, right? What is actually happening is that this transmitted symbol is also received by second antenna. That is also received by that antenna. That's cross channel basically makes interference. Because these two guys transmit at the same time, right? These two guys transmit at the same time. Think about the human, okay? This is user 1. This is user 2. User 3. User 4. Just a simple assumption. Let's say user 1 wants to talk to user 3. And user 4 wants to talk to user 2. But since they are located in the same space, we are all together. So therefore, when this guy talks to this guy, user 2 also hear, right? But user 2 doesn't want to hear that. User 2 only wants to hear user 4. But he hears that, right? Hears the user 3 because of this co-channel interference. So that is the interference. What we need to do is that at the receiver, right here, we bring these two, and we need to take some of the signal processing. And then after the signal processing, you are trying to recover only user 3 message and only user 4 message. You want to separate the user 3 and user 4 after the receiver. Okay? This block, which removes this interference, is called the equalizer. Okay? This is the MIMO equalizer. And including the equalizer, this whole box is called the MIMO receiver. Okay? And there are many different techniques to do this MIMO equalization. Okay? There are many types of MIMO receiver. Some of you who took my MIMO course probably remember some of the equalization technique that we talked about earlier. But there are many techniques. Okay? There are linear receiver, there are non-linear receiver. Even in the linear receiver, there are zero forcing MMSC. Even in the non-linear, there are successive interference cancellation. There are so many techniques. And you see that. So what they do is that they combine this one. They still reuse some of these things and combine with this one with some new system. Like bring this one to the relay, bring this one to the some other type, such as cognitive radio and all these things. That's what people migrate from one topic to another. But this one definitely is a very popular topic and most important topic in this case. And higher capacity. In case of CSI is only known at the receiver, you can take advantage of eigenvalue decomposition. Some of these things we covered actually 2 weeks ago, if you remember. The reason of doing that is try to make 2 independent pipe. Okay? When you do the eigenvalue decomposition, we make 2 independent pipe. Each one has its own eigenvalue, right? So therefore, the reason of doing this is try to make an independent pipe, several independent pipe. Okay? And sometimes we try to use the error rate reduction and low complex design. So some of these things is kind of topic that you can do. And some other people make this assumption. CSI is known at the receiver, at the transmitter. If the channel state information is known at the transmitter, now what you can do is that transmitter can do some more active, okay? Trying to do some more technique. And one of them is called the precoder design. Precoder is a general term. Precoder can be called as pre-filtering, or some people call this a beamforming. It's all kind of in the same category, okay, precoder. And when you do the precoder design, you definitely have to have a goal, okay? You need to have a goal. For any system, you need to have a goal. There can be many different goals, but typically you can think about 2 different goals. You want to design a precoder in order to maximize the capacity or minimize the error rate. Okay? Depending on which goal you set, you may come to the different precoder design. Okay? I'll show you one example, one actual research paper on this one in a minute. And in case of CSI is known at the transmitter, what you can do is that you can play around with the transmit power. You can use a different power allocation, different power for different the pipe, or you can use a different power in the time domain. You can do the many things. And another topic also is the limited feedback. What it means by limited feedback is that, going back to this assumption, right? CSI is known at the transmitter. If a CSI is known at the transmitter, that basically means that receiver feeding back the CSI to the transmitter. Okay? But how is that possible? In order to do that, receiver, actually the typical CSI is a complex value. Okay? It's a pretty big information. So receiver wants to, let's say receiver wants to feed back the CSI, that's going to big overhead. because typically feedback channel is very narrow band channel. Okay, very narrow. So therefore, you don't have a lot of resource to transmit such a information over the feedback channel. Therefore, one of the natural way to do approach is that to study what if we have only small piece of information, small piece of container where you can send the feedback. That's limited feedback. If you want to feedback the accurate CSI, maybe you need maybe 16 bits of a feedback channel. But that's certainly not possible because feedback channel is very limited. Therefore, this approach is trying to find what if we cannot use the 16 bits, but we use only, let's say, 2 bits or 3 bits, 4 bits, okay? In that case, you cannot deliver the accurate CSI, right? Your CSI is going to be quantized, okay? It's very coarse information. But still, it's better than nothing, right? So that's the study. What if we use limited feedback compared to the full CSI? What would be the performance loss, and how much performance improvement you can get, and such things. And also, another type is outdated feedback. This means that typically, when you're feeding back the CSI, it takes time, right? Right? When the transmitter transmits something, that goes through the channel and receiver receives that and feeding back to the transmitter, by the time it takes delay, right? It's one closed loop that needs a delay. So if the channel changes pretty fast, suppose that we have a phase fading, in that case, transmitter now receives CSI value. By the time the channel already changes to a completely different thing, that means it's useless, right? So that's kind of outdated feedback. Okay, that's another type of study. So these things is actually considering the practical scenario. If you think about only very, very ideal thing, then you can simply assume that, okay, I assume the full CSI, accurate CSI at the transmitter, no delay in the feedback. Maybe you can try it that way. That's a theoretical approach. However, it is more interesting to consider this one, limited resources for feedback channel, and also the delay in the feedback channel. Considering these practical limitations is more interesting. So people are looking at those things. There are so many different papers, but let me show you one thing, which talk about a precoder design. So this is a paper, as you see, the optimal design for space-time linear precoder and decoder. Okay, Anna Scalone, she is actually one of the pioneer of this one. And if you look at this picture, let's look at this picture. There are so many different things, but let's see. Here, let's look at this one. The optimal linear design. When you do the optimal linear design, first one is the MMS criteria under power constraint. Whenever you design a certain system, whenever you do optimization, you should have a constraint. Okay? Always the optimization problem has to have a constraint. As I said earlier, let's say you want to minimize the complexity of your system. One of the constraints is that you should not sacrifice your performance. So your performance should be this one. Okay, that would be a constraint. Let's say you want to maximize the performance of your system. Okay, if that's the case, one of the possible constraints would be you have a limited power budget. That could be the popular constraint. For example, right, if you don't have such constraint, then simply speaking, you can increase your power again and again. Definitely, that will give you higher performance, right? That's a stupid design. That's not the right way to do it. You have to fix your power, transmit power, and given that, now you design it well such that you can maximize the performance. Okay, so there will be always a constraint. In this case, under power constraint is like you fix the power, okay, and then you want to apply the minimum mean square error criterion, try to design the precoder. Okay, so that is what they do, and this is the formulation of optimization problem. Always when you talk about system, you start with such an optimization problem. So formulating this kind of optimization problem is probably the biggest thing. How to solve this? You can use some mathematical tools. In fact, looks like they use this one, right? Look at this one. We just covered that one, right? If this value is positive, then you get positive. If this is negative, you get 0. So like a water filling principle. In second section, subsection says that maximum eigenvalue constraint. So you can put a lot of different constraints, try to design a different precoder. Okay? So what I'm showing you is, this is one example that you may want to see sometime later. And that was the capacity. And if you focus the bit error rate, okay, as your performance metric, then we can think about some other things. Like, for example, in diversity, right? In receiver diversity, what you want to do is error rate reduction. Okay, because we choose a diversity, try to minimize the bit error rate. So in this case, bit error rate is our focus. So you want to reduce it, the bit error rate. At the same time, a complexity reduction, if you can, that's possible, then it's better, right? And typically, when you try to minimize the error rate, that corresponds to getting the higher output SNR. When you have a higher SNR, that means lower bit error rate, right? Think about the waterfall curve. It's always monotonously decreasing. So when you have higher SNR, that means lower bit error rate. Okay? Typically, this can be a goal, or this can be a goal. These are the examples. And some people also do the transmit diversity, and one of the popular one of transmit diversity is space-time block coding, right? Alamuri, I introduced you earlier. So space-time block coding research topic is somewhere around here. But remember that space-time block coding and all these things is part of the diversity. So your focus should be to reduce the error. Okay? Capacity is of course you want to get a higher capacity, but that's not your main target in here. Okay? When you look at the space-time block code or Alamuri, all these things, the first goal is to try to reduce the error rate. Therefore, you need to use some of the mathematical tools that we talked about earlier, okay? Using Q function and all these things, right? And using some of the mathematics, integrals and these things. And based on that, you want to analyze the error rate. And for all these things, people have done a lot of work based on a different assumption. The one that I'm showing here is a different assumption, okay, for different things. For example, right, let me give you one example. Let's say I pick MRC as my system, okay? I want to look at the performance of MRC. Maybe the first guy who proposed this MRC make a very simple assumption, right? And then make a performance analysis. That simple assumption could be this one. IID. What is IID? Identically independently distributed. So what that means is this case, right? When you think about multiple antenna system like this channel, and that channel, let's say this channel and that channel, H1, H2. Let's suppose that we have two different channels. These two channels may have a different channel statistics. Okay? Maybe this one follows Rayleigh. Rayleigh has one parameter, right? This gamma bar, average SNR. Maybe this one follows the Rayleigh with a certain average SNR. Maybe second channel follows Nakagami with some other things. In that case, it's completely different that is a non-IID. What IID basically means that both one follows the same statistics, same relay, for example. Not only that, average SNR is also same. Okay? So the exactly same PDF for both of them. That's what we mean by IID, identical. Okay? Not just identical in the statistics, in the PDF model, but also you have the same average SNR. Okay? Both one. That actually makes sense, right? Because think about your cell phone. Your cell phone, you have 2 antennas. And your cell phone, these 2 antennas are pretty much close together, right? So therefore, since these are 2 close each other, if you think about the SNR, that SNR would be same for both of them, pretty much, right? If you have one antenna here and another antenna like 100 meters away, then maybe you can guess that the SNR for both antennas should be very different because we are very far away. But these typically, right, in the MIMO system, these 2 antennas are co-located. Okay? They are separated only by this much. So typically, it is a fair assumption to make an IID. Okay? But another reason is that when you have IID, analysis is much simpler because we assume the same one, so we can make a further analysis with a very simple technique. Okay, so the IID is definitely the first thing that you try. So going back to my previous example, let's say I choose MRC, then I'll probably make an assumption of IID, okay? And no correlation between antennas, branches meaning antenna. And I'm gonna assume a no correlation between 2 antennas, okay? That's gonna be a simple assumption. Then I'm gonna analyze it, error rate. That's gonna be the first approach. If you do that, then the previous Q function, alternative Q function, and those things will help you to do an analysis. Now, let's say that someone already have done that. So you wants to look at the MRC, but someone already published a paper about the performance of this one in IID and no correlation. Then what can you do? You cannot do the same one, exactly same one, right? You have to do it different one. So what people do is that since the previous guy take the analysis of IID case, maybe you try to now make a several different assumption. Maybe using the same system, but now in your assumption is in your case you make a non-IID assumption, or even more, maybe some other guy make a assumption like there is a correlation between 2 antennas. Okay, that's the another assumption, because that's where the novelty comes from. Maybe sounds like a very tiny assumption because we still use the same system, but that's not the case actually. That's that kind of small novelty guarantees, sometimes most of the time guarantees a publication. Okay, it is very rare to bring up a completely new system and do a completely different analysis. That's very rare. Okay? So what I'm saying is that the practical approach. So what you need to focus on is that typically you can think about a good system, whatever system you want, okay? And study what people have done and what assumption people have made so far. Maybe some people IID, then you study, you do a search, and then if no one have assumption of non-IID, that's where you can jump on, maybe, right? Or maybe you can try to make other assumption like no correlation if no one has done it before. Okay? So that is kind of assumption. You change the assumption, that's going to be different topic, as I said. If you remember what I said earlier, right? When you formulate the optimization problem, okay? And then if you change the constraint a little bit, that's going to be a totally different problem. Okay? So even you change the assumption a little bit different, that would be a very different topic. So that would be typically, in practical sense, that would be the most popular approach that a lot of people try when you try to find your own topic, research topic, when you try to make tons of publications. That's what people do. how come the one people make tens of publications and each one is very different system, right? That's not simply possible. So what people typically do is that pick some good system and try to analyze the system from different angle, all different angle. Each one is all different publication. Okay, that's what people do. Okay, and it worth meaning. Okay, that's what I'm saying. And given that, what I'd like to show you is that this is again a very small subset of the papers that is published at IEEE. If you search at IEEE for these keywords, you will see thousands of them, okay? Not maybe hundreds of them. So for MRC case, this is some variation. When I say variation, right, what they mean is that they make a different assumption when you look at it MRC, okay? So this one says MRC diversity with the output threshold. When they say this one, that basically means that they make a different assumption. So when they make a different assumption and looking at the same system, they publish a paper like this. Okay, they have a block diagram and some analysis like this, right? And that's what people do for MRC. And also, MGF is pretty popular when you look at the analysis. This is also another pretty good paper published in 2000 or something, but that's also the area of selection combining. So this is called the generalized selection combining. What that means is selection combining. We already learned the selection combining, right? And what these guys do is that they extended this concept and they proposed a new system called the generalized selection combining. And look at the performance analysis. And when you try to do a performance analysis, they use the MGF technique. Okay, that's what you can see simply from this title. So look at this picture. They formulate some MGF equation like this. Looks like very complex because we have multiple integrals, but this is nothing. Okay, this is just a way of representing. You don't have to worry about such things. And blah blah, they have these things, some of the mathematics, right? And they solve and they show the performance. And also this one is part of the switch diversity technique. And what they do is they do the same way. If you look at the title, this one says analysis and optimization. Okay, so this one is actually just a general switch diverse system, but look at the performance analysis and show you how to optimize it. Okay, and this is the basic diagram, and they introduce a PDF of the channel because we are going to use some of this channel, and starting from the PDF and CDF. Okay, and eventually, when you look at this paper, it looks pretty complex because there are a lot of mathematics. But in fact, what is important is that they come to the MGF or PDF and they use the same technique as we learned, like some BR equations. If you search it somewhere, then you'll see some BR equation somewhere. For example, like this, right? We've seen this one in the course. And also this one. And basically we are talking about all the same equations, even in the journal paper. So all this journal paper, we use exactly the same technique. Okay? And sometimes this is actually one of the my paper. And what I'm just trying to show you is that for sometimes in the switch diversity, for example, I just propose a new system and try to optimize it, right? And try to show you some block diagram like this. And in this case, actually, maybe you can say that contribution or novelty is pretty tiny. You can start always from the very tiny idea. The idea here is that generally in switch diversity, what it means is that as long as my channel quality is good enough, then I don't care. I'm not going to switch, right? That was the case. So what that means is for every single antenna, I'm using the same threshold. But in this case, I was trying to use a different threshold for different antenna because different antenna may have a different channel statistics. So that actually motivates it. And once you make such assumption, then you can bring up some of the simple equation. Then you end up getting some performance analysis like this. Okay. So I'm just trying to show you what people have done and what kind of approach they do to write up papers. Okay, and I don't have it here, but there's also a lot of papers about this. For example, when they analyze MRC, what if we have correlation between the antennas? What if we have non-ID? Each of them is different paper, okay? Then for all the other things. That's what people try, okay, to make papers. So using all these equations that we learned, like these things, right? These things. Or some other integral equation like this. Those are all used when you write up papers, especially for bit error rate. Okay? Any question? Okay, then see you next week.